Yeah, when I was making my PhD 20 years ago, I was really working on a bunch of completely different topics related to testing and DFT. But of course, when we started company, our activities and my activities or my focus has been saturated to certain focus topics. All right. So today I'm going to talk about how you can validate your 1687 IJTAG scan chains and some instruments on FPGAs and what you need for that, and maybe why would you do this. So I will start with introduction to 1687 standard, what it is, why it's needed. I will look through some applications or some use cases in Tessent flow, give you some ideas where you could look at different implementations and different, say, topologies, possible topologies of 1687 benchmarks beyond just EDA tools, what the standard actually itself foreseen, what could be done on top of what EDA tools automatically support. And also I will review 2 case studies of implementing 1687 instrumentation and scan networks on FPGAs. Most of you, of course, know about 1687 standard. It has started 20 years ago when an initiative group gathered in 2004, and afterwards there was a hard work ongoing during 10 years when in 2014 the standard was finally accepted. And the purpose of this standard was to unify access to all the test measurement and configuration instrumentation that you may have on your chip, which is being used for different purposes. So the standard created a way to flexibly access all this zoo of different instruments on the chip. So for applications, of course, testing, including built-in self-test, scan chains, also monitoring, even in-field monitoring is being actively added these days. In-field monitoring, in-system monitoring, IC debug, configuration calibration, and also actually some of those instruments could be used for system level test beyond the chip. So you may have memories on board external to your system on chip. You may have gigabit links. You need to configure transceivers. You want to do memory based. Everything could be done using 1687. Well, the simple idea behind 1687 is that you have a scan chain which is reconfigurable in a number of ways by adding either scan multiplexers where you can either include one or the other path, scan path into the active scan chain, or so-called segment insertion bits where you can either add or exclude certain sub networks of the reconfigurable scan network. And those shift registers are, of course, attached to some instruments which are developed to test some modules on the system on a chip and external to the system on a chip. So simple from the top level perspective, but if we look deeper, then the actual implementation uses a lot of basic elements like scan registers, configuration bits, multiplex control bits, and a very simple network. In fact, looks like this. Here you can see basic configuration elements like scan control bit and the scan multiplexer and the SIB implementation. Automation is the key behind this IJTAG standard. It is based on two description languages, instrument connectivity language, or ECL. It's a way to describe subnetworks of instruments or subnetworks of your scan chains, as well as describe the complete topology of all the scan chains and network implementation on the chip. There is automation behind, which would collect all the subchains together in the top level chain, and the PDL, procedural description language, that normally describes the test procedures or control procedures for a particular instrument locally. They are good to be used together with ECL description to create top level scan, let's say scan instructions. So the PDL will be retargeted, so-called retargeted, from the local instrument to the top level shift operations. All right, so why should I care about IJTAG? So some 10 years ago, when the standard was accepted, it was not well known still in the chip community or chip design community, because the tools were not yet in place to support the standard. And nowadays, the picture is completely different. I reused some slides from the Siemens product overview presentation, and you can see clearly that IJTAG is a way to automatically connect your instrumentation and test data and scan chains through the 1687 access network to external test equipment for different purposes, for testing, validation, verification, and also debug and configuration. So all these procedures, all these functions are implemented by Tessent automatically. So with a little interaction, a little manual interaction from the user. IJTAG also enables the fusion of different, let's say, use cases and technologies, the fusion of the instrumentation and basically everything you need to do around your IC would be actually connected using 1687. IJTAG is also a way to control built-in self-tests and scan chains for all applications like embedded deterministic test, logic-based, memory-based, and so on and so forth. All right, this slide is also quite interesting. My second case study is actually falls in this topic. So it's the mission mode usage of Tessent mission mode enables the embedded system or embedded software actually to take control over reconfigurable scan networks, IJTAG networks, to do real-time monitoring of different parameters on the chip while the chip is running in the field. So it's like doing some measurement in operation. And in our second case, so this this way of working has two modes of operation. So the software from the CPU through the bus can get access to the mission mode controller, which gets access to the scan network and do some reading of the sensors. Or there is a direct memory access also available in this application. And we made another step forward beyond this basically technology, so introducing a third access way into this scheme, where the instruments here, they are supplied with a mechanism to initiate the read operation by themselves. So imagine something wrong happens on the chip while it's in mission. Maybe a checker was actually detecting a fault in some arithmetic unit, in some memory or register, whatever. Could be a parametric fault, could be some problem with the program counter, for instance. Whatever checker you can implement here. When it detects a fault, it's very critical to get the data real time from that instrument, from that checker immediately, because when if we do just periodic reading, we would most probably miss the moment when the fault has appeared, and we miss the opportunity for rapid instant recovery from the fault. All right, so I have a slide dedicated to this case study later on. Right, so let's maybe have an insight into different flavors of IJTAG by looking into the set of benchmarks that implement different topologies of reconfigurable scan networks. So you can visit this address at GitLab, GitLab/IJTAG. This set of benchmarks has been developed. Also, we participated in that, but there was a number of research groups who contributed to back in 2016. So those benchmarks, they implement different IJTAG topologies. They provide equal VHDL schematics and description. They implement all standard features of the standard you can find in the standard. So those benchmarks go beyond the capabilities of EDA tools, because well, there is always a limitation what you can do and what you cannot do, right? Those benchmarks, they implement a complete set of all standard features in 1687 standard. So if you want to validate your tools against the standard, you can look into those benchmarks. Right. So there are altogether 24 IJTAG benchmark examples with different properties, and I'm not going to stay longer on this slide. Just pointing out to the fact that there are different constructs, ICL constructs in the standard, which are, some of them are typical. They would be present in each and every IJTAG design. Some of them are pretty strange, I would say, non-typical. So those benchmarks, they actually have included all of those constructs. So if you want to validate your software against the standard, there is a way to do this using these benchmarks. There's a simple example of different topologies, the same circuit with the same collection of instruments, exactly the same collection of instruments, being connected in different topologies, providing also a different access time to particular instruments. So those instruments which are residing, let's say, lower down on the unbalanced tree, it would take more time to actually communicate to those instruments, while maybe high priority instruments would be located very close to the top level access point, right? So these circuits, again, they have the exact functionality, but different topologies to actually connect the instruments together. Okay. Right. So now let's move to the two case studies where we implemented IJTAG networks on FPGA for two different purposes. So the first case study, the target was to implement reference design of reconfigurable SCAN networks, which is fully compliant to all standards, to 687 standard, to compliant to all practices, industrial practices, and it's fully validated so that this FPGA implementation can be used as a reference, not a model, but as a reference device to validate EDA tools against the actual device. I'm not talking about silicon because it's an FPGA. All right. So, but there is essentially no difference between a silicon and FPGA in terms of accessing the IJTAG instrumentation and SCAN networks, because it uses the same JTAG port, it uses the same access mechanisms, so everything is exactly the same. So if your software works with, if your tools can work with the silicon, they should also work in the same way with the IJTAG networks implemented on FPGA. So we made this reference design together with Advantest to make sure that the tester actually can handle IJTAG networks in the correct way, or the silicon that has the IJTAG infrastructure in the correct way. The second case study, I already mentioned that it's a way to evaluate how quickly we can recover from faults if we have a way to immediately report a fault from the instrument to the operating system, from the instrument to the software, not by initiating reading from software to the instrument, but the other way around. Okay. Right. So if you want to create your own validation environment or a demonstrator, what you can do, what you need to is basically use a simple board with FPGA. In this case, it's RTX7 board. A simple USB cable, USB or USB to JTAG. Oftentimes there is the converter from USB to JTAG already on the board, so you just need a simple micro USB cable to establish your environment. And you need an external PC for test execution. This is it. In terms of preparation of the actual firmware for the FPGA, of course, there are a number of prerequisites or requirements, like if you want to work with arbitrary SCAN networks, then we need to have a way to implement them, both them and the instruments on FPGA. Some parts could be automatically inserted, some parts could be manually modified. Since there is a manual interaction, that's another point or another reason why you would like to actually simulate and validate your let's say design, both in the simulation tools and maybe also on FPGA. But equal could be automatically extracted, and the PDLs, the initial PDLs would be written by hand for instruments, and then they would be retargeted for top-level executions through JTAG. All right. So, and then the implementation of this demonstrator has to involve, of course, the JTAG part and the FPGA logic, where basically all the instrumentation networks actually residing. Right. And then the validation would consist of two parts: validating on the actual FPGA execution, running the SVF based execution on FPGA, and also validating using the simulation. And the two things, they should actually produce similar results or same results. So to initiate these two scenarios, you need to provide equal files, PDL files. Using Tessent, you would receive SVF or retargeted patterns, top-level retargeted patterns in SVF format that would be run by SVF executor, and the IJTAG infrastructure or IJTAG implementation would be placed on FPGA and for the execution. On the software side, on the simulation side, the Tessent again will generate a test bench, and the same IJTAG implementation would be used as an input to the model sim simulator, and we also expect the pass result. So, so if we look at the step-by-step workflow, so first, in order to implement these this work mode, what you need is actually you need to develop your IJTAG network, describe it in HDL, and then connect it to JTAG test success port on the FPGA. You need to develop your instruments using HDL. You need to prepare instrument level equals and instrument level PDLs. Thereby, Tessent would actually do the top level ICL extraction, so connecting everything together, and would do retargeting, PDL retargeting for the execution from the SVF executor. So you need to prepare HDL simulation environment to check communication with instruments, compile FPGA firmware. That's also needed beyond the standard workflow. Establish SVF execution environment using a JTAG cable, and you need some external tool for running SVFs. So either you're doing it on a tester like the Advantest tester, or you can also use some FPGA vendor tools to run SVF, or you can use, basically we use some in-house tools to run SVF over JTAG. So, and everything requires script development as well. So for the first case study, this was the topology, or the implemented 1687 network, IJTAG network, where we had some general purpose registers, but the most important experiment was actually to add switching payload or switching load generators into the FPGA logic. When you turn them on, they apply very high switching load onto the FPGA logic that would consume more power, that would slow down the logic speed, that would raise the temperature. And another part of the network is connected to temperature monitors, voltage supply monitors, to see the effect of that. This could be used for instance, for system level tests. Could be used together with sort of functional test, or together with let's say you can basically run your system level test at the same time as reading data from the IJTAG instrumentation, and if the sensors actually while you execute the test may be executed correctly, so you got your pass results. But while you do measurements at the same time, like measuring temperature, measuring voltage, you may see abnormal actual behavior during the test, and that may be an indicator of some faults that are hidden inside, which were not covered, which were not discovered by just functional tests. So, some sort of indirect discovery of faults. So, and of course, the system level test could be executed at the same time as reading from the instruments or using IJTAG. So it's could be done completely in parallel. And obviously, the expected behavior was observed. So when the payload, the switching load, initially was high, then low, then again high. When it was high, the temperature was high, then lower, then high, and also the VCC reflected the same behavior. So why would you like to implement your instruments on FPGA? Is to probably validate if your, let's say, if your test concepts, if your test instrumentation that you would like to use beyond maybe standard automated ways assumed by EDA tools, would also work, would also provide reasonable results. So it's a way to validate some concepts for you. Another case study I mentioned already. The purpose of this case study was to evaluate how quickly we can actually react on faults that appear real time somewhere in the processor cores. So imagine there is a checker in the processor core, it detects a fault, and if we simply read the status of the checker periodically through IJTAG, we most probably miss the fault. Okay, we need to read the checker diagnostic information from the checker at exactly the same moment when the fault happened, or immediately after. Okay, so for that we appended all the instruments here with the capability to send interrupt requests to the operating system. So whenever a fault is detected, the interrupt request goes to the operating system. In this case, it was Linux running on this FPGA demonstrator, and in a matter of 3 clock cycles, we get fault detection. In a matter of 70, so it's like 74 nanoseconds basically, we get the information about a fault which was detected in the logic before it escalated to registers, before it becomes an error, before it basically starts influencing the functional operations. So before, let's say, before failure, we can take care of the fault and correct the fault. Okay. So this particular demonstrator involved an 8-core CPU implemented on FPGA, and we also inserted over 1,200 different checkers into this 8-core CPU in different modules like ALUs, registers, pipeline, program counter, and so on and so forth. We optimized the topology of the network. So that's very important to have it well balanced, so that the most important checkers would have higher priority to get to send data through the scan chains, while the least significant, so to say, checkers, they would be sitting deeper in the hierarchy. So all these, let's say, project was delivering successful results for the European Space. It was implemented for European Space Agency, actually. All right, so that's practically that concludes my talk. And so here on this slide, I listed well, number of skills that you would require to actually work with FPGA-based validation or environment, establishing FPGA-based validation environment to check your instrumentation and IJTAG scan networks. So starting from development of test access procedures, of course, do PDL, prepare PDL files, perform retargeting, perform test pattern generation, also for retargeting for ATE and JTAG, do the simulation. You need to do the IJTAG network extraction from HDL design, both for component level ICLs or ECLs and the top level ECLs. Then you need to know how to perform IJTAG network insertion into the HDL design. In our experiments, we also needed to do some reuse of embedded instrumentation from the chip, reuse them for board testing, or board level testing, or system level testing. Well, all in all, Tessent was very, very good tool, of course, to work with. When you know how to handle it, when you know how it works, and if you know what you need to achieve. So that concludes my talk. Thank you very much for your attention.